We have seen in previous lessons that this series for the natural log is derived from the geometric series. We have also seen how to use it to compute natural logarithms. It turns out that this is quite an effective approach. For the sake of curiosity, we are going to pursue a different approach today. Consider the function y equals 1 over x. This is sometimes called a hyperbola. The graph of that function looks something like this. For our purposes today, we are interested in finding the area beneath this curve from x equals 1 to x equals 2. That is colored pink. Another way of saying it is that we want to integrate the function from 1 to 2. Why are we interested in this area? Boxed in orange on the right side of the screen is part of the answer to that question. The derivative of the natural log of x equals 1 over x. That is our hyperbola. For the curious, the left side of this screen shows how this expression is derived from the general expression for the derivative of an inverse function. The integral can be thought of as the inverse of the derivative, so integrating both sides from 1 to n effectively cancels that derivative. The natural log of 1 is 0, so that term disappears. Boxed in orange at the bottom of the screen is why we can integrate the hyperbola to find the natural log of a number. Remember that the integral represents the area beneath a curve. We will start by employing the trapezoid rule to numerically integrate the hyperbola. This will give us a numerical approximation to the area, and therefore the natural logarithm. Let's start with 4 panels. N equals 4. The spacing h is 1 over 4, or 0.25. Y is simply 1 divided by the x value. Notice the weight column has all 2's, except the 1's on the endpoints, x equals 1 and x equals 2. The product column is y times the weight. The sum is all the terms in the product column added up. Area is the sum times h over 2, per the expression on the previous screen. Now let's double the number of panels. N equals 8. Everything else follows the same rules as before. We can keep doubling the number of panels, 16, 32, 64, etc. Eventually we get to n equals 128 panels, as seen here. The table is too long to fit on one screen, so here you only see the top part. Go ahead and make your own spreadsheet, compare your numbers to mine and see if they match. Another method of numerical integration is Simpsons Rule. Same approach as the trapezoid rule, except it uses different weights. It is also 4th order instead of 2nd order, which means it gives a better estimate of the true area for a given mesh size h. These concepts are covered more extensively in my lessons on numerical integration, so feel free to check those out for more details. Here is the table for that. It should look very similar to the table for the trapezoid rule. Can you spot the differences? For n equals 8 panels, the pattern in the weight column is a little more obvious. Notice that we still have 1's on the endpoints, x equals 1 and x equals 2. However, everything else in between alternates between 4 and 2. Like the trapezoid rule, we keep doubling the number of panels. We will stop once again at n equals 128 panels. All that data is summarized here. I've highlighted in red the correct digits within rounding. Can you see any patterns? It is true that Simpsons Rule in fact tends to outperform the trapezoid rule, 4th order versus 2nd order. With 128 panels, we get about 10 digits of accuracy for the natural log of 2. Remember Romberg integration? We did a few lessons on this too. Basically, it starts with the trapezoid rule in the leftmost column and uses this pattern to speed up convergence on an answer. We already have data for the trapezoid rule. Following the recipe gives us 15 digits of accuracy. That was with 128 panels. and each panel requires multiple mathematical operations. So we're talking hundreds of operations to get 15 digits of accuracy. The same performance could be achieved with only a small fraction of operations using the series expansion seen at the beginning of this lesson. As I said, integrating the hyperbola is by no means more computationally efficient, but it is a different way of looking at things, and sometimes a different perspective is important. At any rate, it is reassuring to see consistency in the final answer, regardless of which approach we take, whether series expansion or numerical integration. Let us know your thoughts in the comments section below. I appreciate your support and look forward to seeing you again.